Okay, let's get going. All right, so where are we? We are here, November 13th. We're in the middle of discussing analog filters, and then which will lead on to our discussion of how to design IIR discrete time filters, which are, a large and powerful set of filters that you might end up using in practice. The other big class of filters is FIR filters, these all-zero filters, which have a very different design procedure, which we'll talk about starting next week. And then we have we loop back to the DFT, and we examine this particular algorithm for calculating the DFT, the fast Fourier transform, which has a huge impact. It means that a lot of things that would be kind of computationally infeasible we can now do in the transform domain, because there's a quick way of calculating what looks like n squared multiplications to get a discrete Fourier transform, and that has it's this sort of, I don't know, it's this beautiful little thing that just happens to be in signal process DSP, but we'll look at it anyway. The algorithm. I mean, it's not, the reason it's beautiful is not the same basic stuff as the other things we've been looking at, but it's a good opportunity to look at something like that. And then we'll have just a little bit of time looking at issues of interfacing to continuous time, basically what happens with sampling and aliasing when we do have real-world signals that have bandwidth that exceeds our limited discrete time bandwidth. And then the final class will be project presentations. Again, these are not obligatory. We'll only have time for like 4 or 5 or 5 or 6 of these, but there's always an interesting thing. There are always some projects that people want to present that have interesting results, and so it's really nice to see what people come up with. Our final exam will be a week after that, on Monday, December 16th. It'll be here at 9 o'clock in the morning. I'm saying 2.5 hours. Because that seems like long enough. Although, as I've discussed with some of you, I'm not that interested in whether you can do these questions quickly. So I'm happy to give you we have like a 3-hour slot, but it'll be something like 2.5 or 3 hours. And hopefully the limitations won't be in time on what you can do. So that's just where we are. We've only got a few weeks left, which you probably already know, but just, to make that point. In terms of the final exams, I know maybe some of you are wondering what that's going to look like and, how you're going to do. Just to help give you a bit more information, I've posted now the finals from the past 2 years, so you can see what they look like. They're typically, it's like 4 questions with multiple parts, and it covers, a lot of it is covering the filters that we've learned how to design in the second half of the semester, but it also draws on the sort of general principles of discrete time signal processing analysis that we covered in the first half. So it's, because you can't really do one without the other. So you'll get an idea from these. Last year, I managed to completely mess up the question, so that the actual question was meant to be something about this, which is actually a discrete cosine transform. I left out the plus sign, so it looked like these 2 terms were multiplied together, which was something completely horrible. And I don't know how that managed to slip through. It was like, I think I did actually run it by the TA, but because this is this structure is familiar, he knew what to expect, and so he didn't notice it either. So we'll try and make sure that doesn't happen again, but just you'll see that when you see the solutions. It's like I end up trying to write so this is what happens. If I do this, it's like, well, that wasn't the question I meant to ask, but okay, we'll see how that allows you to display your knowledge of signal processing. So it's possible to answer this question, but it's not a very interesting question to answer, because this is some crazy system. But we'll try and avoid that this year. Okay. So, I guess you all have your midterm grades now. Hopefully you are able to pick up your your graded midterms from Darwin yesterday. Sorry that it took us a little time to get those back to you. I haven't had any comments or discussion back. If you do have any issues with how it was graded, then let us know as soon as possible. I'm sort of holding off on releasing the solutions until we know that we've got all that stuff taken care of. But if I don't hear anything by this afternoon, I'll post the solutions as well so you can see those. Okay, so with the second half and the end of the class, we also have the consideration of projects. So as you know, the overall grade is like 20% midterm, 20% homeworks, 30% final, 30% project. So the project is a very big deal, and it's a good opportunity for those of you who maybe feel like exams don't give you the chance to show your real capabilities to show what you can do in a situation where you get to control it more. As I've discussed, the goal of the project is to expose you to some of the broader issues that come up in practical uses of signal processing. So it's the only thing I really want to see is that you've actually gotten to work with a real signal and solve some kind of real problem. And there are these things like sometimes in a signal processing problem, it's like, it's okay, we just have to design this filter with these, with these gain response points, and we're done. But of course, that's never it. It's always like, well, you've got to embed this in some larger thing, and you want to have that filter so you can solve some particular problem. The idea of the project is to look at those parts a little bit more. So it's like, okay, there's hopefully some core of the applications of the techniques you've learned in class, but it's like you're doing the whole thing end to end. So you're actually trying to solve something specific using these techniques, and then you can see how well you do. And so also it's important to me that you work with a real signal. That is, I don't want to. You could imagine a situation where a valid project would be something that was purely theoretical, just deriving something or proving something. But that's not what we're looking for here. I'm looking for something where basically you have some data in MATLAB and you process it and you do something with it. And ideally, that data would be something that comes from the real world, because of course one of the things that comes up is that we have these nice mathematical tools. They rely on certain assumptions about what the behavior of the real world is, and those assumptions are usually wrong. And so sometimes you can get an interesting insight into that by working with real data and then seeing why it didn't exactly turn out like you wanted. Basically, there was some aspect. Typically you might have some assumption about noise, that it's just uncorrelated white noise, but the real world noise has got more structure than that, and that can mess you up. So it's great if you've got access to real data that you can use for this, or you can collect it yourself. Obviously, in some cases, that's not possible. If you want to do a project on, space telescope signal processing or something, then you're not going to be able to go and collect your own data. So it's okay. And also, sometimes, if you want to investigate how your project is working, real-world data will often be uncontrolled. It's like you can't control the level of noise. And so sometimes it's useful to be able to synthesize data where you take signals and you modify them, add noise, add them together in such a way that you can exactly control the properties of that data. Then you can see how your algorithm works on that. So there's room for synthetic data, but I don't want it to be, too simple a case. If I just take a sinusoid and I add it to white noise, then that's basically something that, has a closed form solution, the analysis of the optimal detector for that or something like that. And so that's not, we can verify that, but it's more interesting if you have noise and signal conditions which are not too simplistic, that have sort of some of the real world complexity that, is really what this is all about, what we're going to do with this. So I've had some discussion with email and some of you about these things. If you're limited to using synthetic data that you construct yourself, that's okay. But please put some thought into making it interesting and as realistic as possible. So there's a page on the website here about the class project, which basically just talks about those things that I've just said. I've just added this to it. So in the past, I've said you can just report, you can write your report however you like. and preferably not too long, so about 5 pages around there. But I've just added this set of 8 headings, and I'd like you to use these headings. And so basically, these headings are a kind of sketch of my idea of what an ideal engineering project should be like. So you start off with a clear specification of the problem. I want you to describe what data you're using, just because the data is important. I want you to describe what evaluation you're going to use, because the evaluation is important. Then describe your approach, the results of when you apply your approach to the data, and then when you use the evaluation criteria, and then an analysis of what happened. That's kind of the most important part. I guess there are 2 important parts. One is how you actually went about solving the problem, what your approach was. And then the second is, well, whatever the approach was, you got some results. Can you make sense of it? Because that's really how you're exhibiting, that you've actually got facility with these techniques, that you get some results out, and you can say something sensible about what happened. It's not so much like, did it work? Because if it just worked, that wouldn't leave you very much to say. It might be quite an impressive thing to do, but it never does really just work. It just means that you're testing it on something that's too easy. So it's very much like, okay, here are the limits of its ability to solve this problem, and then what can you say about why these are the conditions where it starts breaking down. If you have the chance, then it's nice to carry on and look at the results here, do the analysis of the results here, and come up with an idea about how to improve it to try and see if you can fix those problems. So classically what happens is, you build your system, you run it, it has some problem with some particular cases, you think, aha, that was because I hadn't, you do your analysis, I didn't realize this was going to be a problem, but now I see the result, of course this was going to be a problem. That's great, that's engineering. So then it's like, well, if I twist the algorithm like this, I can fix this problem. You do that, you try it, you go back, it fixes the problem, and then it breaks something else. Like, that's a classic thing, and that would be a nice, that's just how it works. And so that's kind of, again, it's a good lesson to learn. And if you can write a project that has something like that in it, then that's fine. And the fact that it broke something else, maybe you changed it and it got worse overall, that's fine. The point is that you're thinking about what happened and you're trying to change it in a appropriate way, and then being able to measure what happens when you do that. And then finally, just conclusions, just to summarize what happened and what you learned about what you learned, and perhaps what the world has learned about how to solve these problems. Right? That's the reason we do research like this. So I'd like you to actually use these headings. It's a little bit artificial, and it's not particularly. I don't think it's I don't like imposing arbitrary constraints on you, right? But I think in this case it would be helpful just to make sure that, if you can't fit your project under these headings, then maybe there's a problem with the project. If you feel like, well, no, I don't think there's a problem with our project, I think there's a problem with your headings, then that's fine. Tell me about it, and we can agree some exceptions. But without that, please use this structure. The rest of this page has these project things which have been up forever, and so I don't want you to set too much weight by these. These are just a set of ideas that I came up with once a few years ago, just to sort of get you thinking. But I'd much rather you did a project which was completely of your own design, and that this is more important. This part of the page is more what I want you to pay attention to. And then there are a very small number of projects, example projects these are from 2010, I think, that you can look at to get ideas about that. When we look at the structure of the course, we've only got a few weeks left, so now is the time to be doing your projects. One of the things that can go wrong is that people choose a project which is sort of somehow it's too ambitious or something like that. But most often that's the common thing, that it's like, oh, I want to build a system that's going to recognize speech. Be great, but it's once you know how much effort that's gone into that and how difficult that problem is, then you realize it's not such a great thing to try and do in a couple of weeks at the end of the semester. So I would like you, once you've chosen a project or if you've got an idea about the general direction of your project, send me an email or talk to Darwen, just so that we can give you some feedback and make sure that you're on the right path. But now is the time to be getting to that point where you know what project you're going to do, because we've only got a few weeks left, and this is about the appropriate amount of time. We've still got problem sets going on, so there's another problem set today, but it's really just a couple of questions and their MATLAB variants, and so the problem sets from now on will be, hopefully a little bit easier and quicker to get done, so you can spend a good chunk of your time working on your projects. The project report is due on the Monday after the week, 1 week after the last class, which is Monday the 16th, which is also the date of the final. The date of the project report being due is not super critical to me, but it's helpful to have a deadline. If it would help you to have an extension, then I'm willing to grant an extension as long as you provide me, tell me in advance and tell me when you're going to submit, just so that we don't let things get open-ended and carry on forever. Any questions? Yeah.
Does it have to be MATLAB-based?
Does it have to be MATLAB-based? It doesn't have to be, but I remain to be convinced that there's a better alternative. I really like working in MATLAB for these kinds of projects because, you can write a few lines and you've got something going. If you try and write it in, say, C++ or something, then you have to worry about all the problems of, loading in the signals and displaying them and stuff like that. So MATLAB is a very nice environment. And of course, limitations of MATLAB are things like, well, maybe it doesn't give you the greatest efficiency, doesn't integrate with other systems so well, but they're not really issues here. The chances are that you're not going to be computation time limited. Recently, research in my group has been moving towards Python, and I'm very interested. I think Python is a very good competitor to MATLAB, but it's still not, for me anyway, it's not quite as convenient. If you don't want to use MATLAB, then again, check with me and I can give you some feedback on whether I think that's okay. Any other questions? Okay, good. Well, like I say, the projects are, for me, a really important part of the class and can be, a nice balance to the more programmed theoretical material we're doing in lectures, where you actually get to do something that's interesting and relevant to you. So please make the most of that, and I hope you enjoy it. Yes?
Should all the codes be original?
Oh, good question. Thank you. Should the codes be original? That's a very interesting point. And because, of course, if you're going to solve any kind of simple project, the chances are that there's some existing code out there which will be relevant, which you might want to draw on. If there is existing code out there, but you want to do it yourself, that's fine. If you want to look at existing solutions out there to get ideas, that's okay too, but just make sure that you just be explicit about that. That's how we do engineering, right? It would be silly if I was teaching you that the way to do engineering is always you have to solve a problem by yourself. Right now, there's lots of source materials, and a natural way to solve a problem is to see what's out there. But at the same time, here's the problem. If you say, okay, I want to do beat tracking, and then you go out there and there's like a ton of different beat tracking systems, and some of them are pretty sophisticated. And it's like, okay, well, I guess I have to start from this, and I'm going to have to change one of these. That can make for a much less clean project because, rather than just starting with a simple idea and trying it out, if you have to figure out someone else's code and work with it, that's just a very different thing. So if you want to solve a problem that there are existing solutions out there, go ahead, do it however you want. Either take advantage of the resources with due citing in your report, explaining how you've done that, or don't and just do it from scratch, and that's fine if you're interested in pursuing an idea. If you want to build something based on existing code that's out there, that's fine too. Again, make sure it's very clear to me what you've used. And the thing that works less well is like, okay, I'm going to take this, this sophisticated machine learning package and this existing feature extraction package and just plug them together, because then there's not very much opportunity for you to actually use any kind of signal processing knowledge. It's like, okay, someone else has figured out how to do denoising, and I'm just going to use their thing. So I wouldn't encourage you to do that. If it's that kind of situation, it's better for you to actually, implement your own version of the denoising or whatever like that. But if it's like, I've got this interesting problem, but I need this feature pre-processing I've got this interesting idea about how to modify something, but it requires some existing feature extraction, go ahead and use the existing feature extraction and then, build something else on top of that. That's fine. I do need to say that in the past we've had problems with plagiarism, that is using other sources, existing online resources, as the core of your project without properly acknowledging that that's what you've done. Please don't do that. It totally, it defeats the whole purpose of what we're doing here. It turns me into I suddenly become, a policeman trying to or an investigator trying to figure out where these things have come from, rather than, what I want to be, which is just teaching and then evaluating how you're doing. It is the case that people who tried it in the past have not gotten away with it. Of course, I don't know. There may be people in the past who tried it and have gotten away with it. But sometimes it's kind of obvious that, I can see that there's kind of this particular, unevenness of style, which makes it obvious when things have been pulled from other places. And often with code, it's amazing how much you can read into code if you, once you're used to it. So I can usually tell if code has come from an unexpected place. And it's amazing how much you can tell even, people who've tried to disguise it by changing variable names and stuff. There are things in the algorithm which are, the whole idea of forensic code analysis is actually a really interesting thing. And it's one of the things I've gotten into from doing this that I wouldn't otherwise have done, just because you realize there are all these individual choices you make when you write a piece of code that it's just like that. There's no way that would have happened by coincidence. So my assumption is that we're all not thinking in those directions, but just in case at some point, here's how I imagine it happens. It's like, oh my God, it's a week before the end of class, I need to get these projects done, what am I going to do? And it's like it's a blind panic situation. Don't be tempted to take the dark path of submitting work that isn't your own work. If that's the situation, I'm so much more interested in having you do work that's correct and having you actually, that's done the right way and having you go through the valid learning experience. I'm prepared to be very flexible about, submission of projects, whatever, but please just, do it, be honest, do the actual work that's your work and give me the stuff that actually reflects what you're doing to grade. That's not quite, that's a little more answer than you were looking for, but that's an important point to discuss. Okay, any other questions? Okay, so we're talking about how to design filters. We're working towards how to design IIR filters in the discrete time domain. But I've said the way we do that is actually through a transformation based on these analog continuous time domain prototypes. And so we're learning about the sort of the standard canonical ways of building analog filters, which are these 4 different classes of filter that differ in whether they are flat, meaning monotonic, or whether they have ripples in the pass band or the stop band. The first one, and we talked about the analogies between the continuous time filters and discrete time filters. They both have this transform variable, the S Laplace variable or the Z transform variable, and meaning that the systems are described in terms of polynomials on these transform domain variable spaces, and so we can talk about representing those polynomials by their roots, by the poles and zeros in the transform domain, and that that's a very quick way of understanding what the filter is doing. The difference is that in the Z-plane, the Fourier transform, the actual frequency response is the values on the unit circle, magnitude Z equals 1. In the Laplace domain, the values of the Fourier transform are also a set of points, but they're the points on the imaginary axis, h of j big omega. And poles for stability, for causal, for forward in time stability, poles are going to be left-hand half plane here, whereas they're going to be inside the unit circle here. Okay, but now we're switching to the analog domain, so we've got big omega. And the first filter we look at is the Butterworth filter, which has this monotonic function, which always the gain, for a low-pass filter, the gain always gets smaller as frequency gets larger. And we can analyze this in various ways. And then because we have an actual expression for the magnitude response, we can then figure out the parameters for the filter that will meet particular design constraints. So we can figure out, in particular, what order of filter we need to achieve a certain stop band attenuation, pass band ripple, and transition band width. And so it turns out these filters actually have these poles, which presumably if we went through the process of figuring out exactly what h of j big omega was, we would see that it worked out to have this magnitude response that we saw, although we didn't go through that. We just take it as we take it for granted. And then we saw that we could, from a specification like this, we could come up with the filter. Turns out that to get this drop from 1 dB to 40 dB in a ratio of 5 to 1, we need to have a Butterworth order of at least 4. And so once we got the order, then we can basically fit some tables and find out the exact parameters, the exact 3 dB point or whatever, the particular filter that we need. There's only one fourth-order Butterworth filter, basically. They all have the same shape, but we can just scale what the frequencies are to make sure we get inside our constraints. But we can work out that filter, which we typically do just by scaling, because scaling a filter is very simple. Scaling the frequency response of a filter is very simple in the continuous time domain. But, of course, we can also just get MATLAB to do it for us. So that's in practice what we do is this is what's going on under the hood. We don't need to go through the bother of that. We can just use these convenience functions in MATLAB. I've never actually looked at how Butter is implemented, although presumably I assume it's actually written as a script you could look at. But it's going to be doing something like this. It's going to have basically some function, which is the 1 over 1 plus omega on omega c squared, and it's going to solve that to get particular values out. So that was like our first analog filter, the Butterworth filter, which is, hugely important and a very widely used filter that you'll come across, but also pretty simple and not particularly dramatic in its performance. It has a fairly slow roll-off because you've got this nice property of monotonicity of the gain. The second class of filter was, okay, now we're going to start introducing ripples. Here we're going to have ripples in the pass band, and this is the Chebyshev 1 filter. Chebyshev was a Russian mathematician in the 19th century. This is his name in Cyrillic. Because of that, we can't quite figure out how to spell it in English, and this is how we do it now. But originally, it was spelled with a T in front. It's like Chebyshev rather than Chebyshev. And so we have this variable, this function, which is the Chebyshev polynomial here, which is it's this way of merging together a cosine and a hyperbolic cosine. So they sort of, in the range where cosine is a valid thing, it's cosine, and then outside of that range, it becomes cosine hyperbolic, and it's continuous in slope. I don't understand the math behind this or how you can pull this off, but anyway, this function exists. We can make systems that have this behavior, but the actual, once you've got this function, then the way we use it is like this. And now we've got something which looks quite a lot like the Butterworth magnitude response. It's a magnitude response as a function of omega on some reference frequency, in this case omega p, 1 over 1 plus epsilon, 1 over 1 plus that something. But what we've got is this Chebyshev polynomial, nth order for an nth order filter, and an epsilon squared here. This thing, the properties of this thing is that it oscillates between 0 and 1 for omega less than 1. And so for smaller values of omega, this thing is going to vary between 0 and 1. And so this whole gain term is going to vary between 1 and 1 over 1 plus epsilon squared. And that's going to give us these ripples in the pass band. And then for large omega, this thing just gets large. And so we get this nice monotonic fall off of gain in the stop band. the number of ripples that we see is going to relate to the order of the filter. So that for a low-order filter, we just get, I guess, n on 2 ripples in here. And for a higher-order filter, we get more ripples, but we also get a more rapid decay as the filter goes out, which is a better low-pass filter here. The parameter that we care about, if we're going to have ripples, then we maybe want to be able to control how deep these ripples are. And that's controlled by this epsilon here, at least in the equation, right? If epsilon is close to 0, then the amount of that this varies away from 1 is going to be small. As epsilon gets larger, the ripples get deeper. And basically, as we make the ripples shallower, we're also going to make the roll-off shallower. So it's like, you can trade off. You can make the ripples as deep as you want, or as not as shallow as you want, but you're going to have a less rapid decline as you go outside the frequency range. So that's the general idea, that we have a filter that's got ripples in the passband and monotonic gain decline in the stop band. Just to give you a little bit of insight into what's going on, this is the Chebyshev polynomial. Here's what it looks like if I actually plot it out. T sub 5, so fifth order Chebyshev polynomial. Between 1 and minus 1, it's the cosine of n times the inverse cosine of omega. So if n was 1, it would be the cosine of the inverse cosine, which would just be y equals x, straight line. But for n larger than 1, which is the case we care about, we take the value, we find the angle that would correspond to, inverse cosine, the angle that would be the cosine of. We multiply it by n, right? So basically, because it's an angle, we stay within, one revolution, but we sort of go through those revolutions n times. Then we take the cosine again. And so that gives us this kind of shape here that wants to be y equals x, but then it's sort of y equals x through a cosine and through n cycles. And so it has this thing. But it isn't cosine because it's the actual basis itself is from inverse cosine. So it sort of gets squeezed up at the edges. It's like n on cycles of n on 2 cycles of a sinusoid, but sort of compressed towards the edges. And then beyond omega equals 1, it shoots off as this hyperbolic cosine thing, which, is e to the x plus e to the x, what is it? E to the x minus e to the minus x, something like that. That's the Chebyshev polynomial. What we're actually doing in this response is we're squaring it, so now it was between 1 and minus 1 in this interval, and it becomes between 0 and 1, and then just becomes large and positive outside of the interval. And then we take 1 over 1 plus some small constant times that, which means that, now these values around 0 become values around 1. These values that are shooting off become values around 0. And then the actual depth of these ripples in here depends on this epsilon squared value here. So this looks like our Ripley magnitude response, but that's how it comes out of this Chebyshev polynomial. Again, the question is, well, this is one way of plotting a function which looks kind of like I wanted, to a filter with some ripples in the passband and monotonicity and stop band, but can I actually have that filter? Again, we haven't derived that or proved it, but it turns out, yes, we can build these filters, and that's why we're looking at this math. Yeah.
That was an omega versus amplitude, right?
This is omega, yeah, and this is just the function here. I mean, this would actually be the magnitude squared function, right? By definition, it's the thing from the top right. But, yeah, it says omega here. I'm sorry, it's so small. Okay, so given the existence of these things, how do we actually go about building a Chebyshev 1 filter? Well, basically, if the specification says, okay, I want to make this low-pass filter, here's the amount of ripple we can tolerate in the passband, then that passband ripple gives us epsilon, right? Epsilon basically says, okay, that's 1 over 1 plus epsilon squared is going to be the smallest squared gain in the passband, so we set that. If we then also have the minimum stop band attenuation and the stop band edge, we're basically going to have to up the order of the filter until we the fall off is below the minimum attenuation in the stop band edge. Once we get, because it's monotonic in the stop band, it's going to keep getting even lower as frequency goes up, but we just have to hit that one corner, and we have to keep upping the order of the system until we hit that corner. To calculate our order, again, we basically do the same thing of plotting that curve, calculating the points, and trying to solve for n coming out of this. So, we have the stop band attenuation as the expression, the magnitude squared expression at the stop band edge here, which we can plug in, the Chebyshev polynomial, and we rearrange, and you end up with this equation here. Now, this equation here looks a lot like if we look back to the analysis for Butterworth, this was kind of like that. It was the log 10 of this thing, which is the inverse discrimination, divided by the log 10 of this thing, which is the so-called selectivity. But here, instead of log 10, it's inverse hyperbolic cosine. And the point about that is that, well, it's the ratio of these things, so it's a little bit, the absolute values don't make any sense. It's not half of that. But it's the same, but it's the ratio of these two things. And that this thing grows more slowly than log, right? So that actually, if you plot the log of x, it looks like this as a log of some parameter, right? This is our performance and this is going to give us n, right? It's going to be, when we calculate this thing out, we're going to get a lower bound on n. And so saying as we increase the performance, we increase the, reduce the ripples or increase the stop band attenuation, n grows, and for a Butterworth, it grows more or less as log. For a Chebyshev filter, the function here looks kind of like this. It actually pokes outside of here for a little bit, but then it goes back under. And so we're saying for a certain high-level performance, the Chebyshev filter is going to give us a lower order to achieve that. They're different filters. That's what we expect, that we've allowed ourselves to have ripples in the pass band to basically allow us to either get better performance for the same order or use a lower order for the same performance. But here's the closed form equation to decide n, and then basically when we do it right, when we build that filter, it'll have the right performance. So what is the actual, we might be curious, how do we build these filters with ripples in them? Like I say, I have no idea. If you just gave me that Chebyshev magnitude response and said, find the filter that has that, that seems like a difficult math problem. But I have a MATLAB function that'll do it for me. And so then once I'm given that polynomial, I can firstly verify that it does what it does, which it does. I can also find out where its roots are, so I can see what the actual performance is. And this is what you get. Remember, for the Butterworth polynomial, for the Butterworth filter, we had these poles on a semicircle. For the Chebyshev filter, they're the same poles, but now the real part has been scaled in, right? So you see they're if we stretch them out to touch the circle, they would be uniformly spaced around the circle. When we scale in the real part, they end up being more bunched up towards the 3 dB frequencies here, and they're obviously much closer to the Fourier axis, to the j omega axis. And so that makes sense that when we put these poles close to the axis, we expect to get ripples, right? Because we expect that, well, in here, this pole is much closer than all these other ones, so there's going to be some local peak in the magnitude response. But it turns out that by arranging them like this, we can make it so that all these ripples are equal depth, which is not at all obvious from looking at it. They're all going to be the same depth. But that actually works out. Yeah.
Are the two, the topmost and
Yeah.
bottommost pole, is that directly on the imaginary axis?
No.
Okay, cool.
So they're certainly not on the imaginary axis, because then they would be unstable poles.
Okay.
But they're not even on the unit circle. The circle is actually the circle at radius omega p, I guess, the pass band edge. I'm not sure about that, but it's something like that. But they're very close. The last pole is very close to the pass band edge, but not exactly at it. So you see here, in this magnitude response, the passband edge is here at 1, and the last pole is going to be somewhere around here, just a little bit before that. I mean, say. Okay, so that's, like I say, we're basically doing a little skim off the top of this fairly serious theory, but it doesn't matter how the theory works. We've got the result, and we can just use it now. The third kind of filter is the Chebyshev 2 filter, which is the complement of the Chebyshev 1. Chebyshev 1 had ripples in the passband and monoticity in stopband. Here we have flat monotonic gain in the passband, but then we have ripples in the stopband. And so the main parameter we choose now is like, well, how large are these ripples in the stopband? The gain in the stopband is going to alternate. It's going to go between 0, right, at these points here, and some maximum. We're going to choose the maximum. And then once we've chosen that, we can set some criteria on how far we let the passband go down and how wide we want the transition band to be, and we can control those through the order of the filter. The polynomial looks like this. The magnitude squared response. It's 1 over 1 plus epsilon squared, but now it's this thing, which is a normalizing constant, the Chebyshev polynomial for the stopband edge on the passband edge, divided by the stopband edge divided by frequency. So here's the actual dependent variable, the omega in here, and it's 1 over 1 plus epsilon constant divided by Chebyshev of 1 over frequency. But this is basically, if we thought it through, this would do what we want to do. That is, now we're using the long monotonic part of the Chebyshev polynomial to give us the flat part in the passband. I'm using the ripples, the part where omega gets small, omega is smaller than 1, to give us ripples in the stopband like this. Interestingly, we notice that here we've got in the stopband the gain is going to 0 for some finite frequency. In the Butterworth and the Chebyshev 1 filter, the gain got smaller as you went up with frequency, but it never quite got to 0 until you got to frequency equal infinity. And so there were no zeros that we could identify on the pole 0 diagram. But here, these frequencies are frequencies where the system has a gain of 0, which means that there are zeros on the pole 0 diagram. So this is a system that has zeros, which we hadn't seen before. But that's basically what happens when we start taking the that by constructing the magnitude response like this, you end up with zeros in the full polynomial expansion of this, of h of s. And the overall pole 0 diagram is pretty complicated, so it's not particularly, you don't really get that much insight by looking at it anymore. I forget what it looks like, but you can look at it, right? You can do the same thing, use the MATLAB function to build the polynomials, and then do z-plane or whatever to plot the roots of those polynomials, but it doesn't give you that much insight into how this thing's working. And then finally, the fourth kind of filter is with ripples in both the passband and stopband. That's called an elliptical filter, or sometimes a Kauer filter. Here's an example of the response. And so it looks like, the stopband part, the passband part of the Chebyshev 1, and the stopband part of the Chebyshev 2. But it has both of those, and of course, by virtue of allowing ourselves ripples in both parts, we can get some filters with extremely rapid transition bands here. We've got a pole here, right near to the edge, giving us that last little peak. We've got a 0 here, just a little bit larger than it, pulling us down very rapidly to a low gain. And then everything else is balanced, so these ripples are equal depth, and we can get these very high-performance filters. There is an expression here for the magnitude squared response, which again is 1 over 1 plus epsilon squared something. But this function is not particularly nicely behaved. It does have this property that the function of the reciprocal is the reciprocal of the function. That means that if we have values for which this function is 0, then it's going to be infinite for the reciprocals of that point. And so that's what happens here, is we end up with these reciprocal positions of the poles and the zeros. Like if there's a pole here, a pole somewhere around here, it's not exactly here, but there's a pole somewhere around here at omega equals 0.4, then there's going to be a 0 out here at omega equals 1 over 0.4, 2.2 or something. 1 over 0.4 is something a little bit more than 2. This one here at 0.8 has a corresponding pole, 0.9 is a corresponding pole at 1.1, say. So this is, but these things, they exist, and we've got procedures for designing them, but mathematically they're pretty nasty, and there isn't even a nice expression we can just plug in to find n. Basically, it's it's iterative. If you have some constraints you're trying to match, you build the filter for a certain n. You see if it meets the constraints. If not, you then increase the order by 1 and redo it. Of course, typically you don't have to search that many times, but it's not something where you just get a result out. So here are, in summary, the 4 different filter types, the 4 different analog filter types we've introduced: Butterworth, smooth; Chebyshev, ripples in the pass band; Chebyshev 2, ripples in stop band; elliptical, ripples in both pass and stop bands. To compare them, I've used the same order here. These are all 6th order filters, and I've tried to use the same kind of constraints on the pass band and stop band. I've used a pass band ripple depth of 3 dB, and stop band attenuation of 40 dB, minimum stop band attenuation. And you can see that, using equivalent constraints, the performance gets better. In this case, the thing we haven't limited is the transition bandwidth. So here, this thing gets down to 40 dB at like 2.3 times the passband edge. This one gets to it at like 1.4 times. This one actually is sort of about the same. It's 1.5, and maybe the gain is a little better than 3 dB here. But this one here, the transition band is tiny. It's like 1.05 or something. So you get a much sharper transition. The price you pay here is you've got ripples. I mean, these are actually 3 dB ripples is fairly severe ripples, right? You've got variation between 0.707 to 1 in the pass band. So that's quite a lot to pay. And so you can't always get a transition band this wide. The other price you pay is that you've got poles and zeros right there, right around your transition frequencies. You have much more severe phase effects for this kind of filter, particularly around the band edge, but also in here. We've got poles hanging around, making weird phase things happen in the frequencies. But for a 4th order filter, they're not going to be that severe, and this is a really nice low pass filter. Any questions about that? Okay. So that's great if we want to build a low pass filter. As we know, there are other kinds of filters that we're interested in, even just with the simple filters. There's high pass filters, and then band pass and band stop filters that we might care about. It would be kind of a pain if we then had to go through and have new formulae and new procedures for each of those filters as well. Luckily, there's an alternative approach which is based on this idea of transformations of the transform variable. And so we'll look just at the high pass version just to give an idea. And so the basic idea is you define a transformation of the variable in your polynomial as some modified function, some function of the original one. And so basically you can take your polynomial and you can substitute in, wherever you see s, you substitute in s hat, and you get a new polynomial out, and that's great. And then the trick is to do this in such a way that when you do the transformation from s to s hat, you end up modifying the actual frequency response of the implied system in a useful way, so that you've got the frequency response that you want, and you've still got a stable system. So that means but we can think of this as a mapping between two planes, a mapping from all values of S to all values of S hat. And so wherever there were poles under S, they now become poles under S hat. The same with zeros, they're just at new points. But the point is, well, we want to make sure that our poles all remain stable. So that means we want the left-hand half-plane, all the values that correspond to the left-hand half-plane S to remain values in the left-hand half-plane S hat. So the poles end up staying stable if we start off with a stable system. And we want the frequency axes to map to the same frequency axis. So we want all the points for S equal j omega are these values of magnitude response that we've carefully constructed. They've got this particular property that they have equal-sized ripples, if it's one of those filters or whatever. They have this nice, or they have monotonic decline for the flat parts. We'd like to keep those as the frequency values, but of course we want them in a different order because we want to change from a low-pass filter to a high-pass filter. And so that's the idea of this transformation, something that'll keep the filter properties that we want, but allow us to control what's happening with the filter shape. And so for a low-pass to high-pass transformation, it's this, that you take your low-pass filter, which is as a function of S, a rational polynomial in S. You substitute this, which is basically some constant divided by S hat. The constant is a product of the passband edge of the original filter and then the passband edge you want for the high-pass filter, which will, of course, be the lower edge of the passband rather than the higher edge. Have that constant divided by S hat. You substitute that in, you get a new polynomial here, and this polynomial is going to be the high-pass polynomial that we want. And so, we'll rearrange it, but when we rearrange it, we're still going to get a rational polynomial now in S hat with, I think you can see it's going to be the same number of poles and zeros, because, if the highest order of S in the numerator was n, then what we're going to have is now a numerator that's powers of S to the minus n, but S hat to the minus n, but it's still going to be the same order once you scale through by the, top and bottom by S hat to the n. But the question is, okay, so we've got this S going to 1 over S. What actually happened to the frequency response? Well, to understand that, we want to know that for the points in the original transfer function that were the frequency response, that is, the values S equal j omega, the values on the imaginary axis, where do they land up in the mapped place in S hat? Well, we're saying that S hat is omega hat p divided by S. S is j omega. So the S hat is going to be j times minus omega hat p divided by omega. So the minus comes from, because the j goes from being on the bottom to the top. But the point here is that the values that were on the imaginary axis, in theory, in general, they could land up anywhere in the imaginary plane, but they still land up on the imaginary axis. Right? They could have been anywhere in the complex plane, but they're staying on the imaginary axis, which is the critical thing, because these are the points where we constructed h of s to have particular values. And so now, these are the values that we care about, the transformed h of s. And they're still the same values, but they're now in a different frequency point, which is, if they started off at frequency omega, they land up at frequency negative k divided by omega. For omega equal omega p, if we plug in omega p here, then the actual omega p maps to omega hat p, or the negative omega hat p, but the plus and, normally we have things which are symmetric around 0, so the negative sign isn't that important. So that's why calling it omega hat p is the right thing here. It's the point where the passband edge gets mapped to. But for frequencies below that, we end up with these frequencies which are going to be more negative than that, so they're sort of beyond the passband edge. And frequencies above that in the original high-pass filter, we end up with frequencies which are smaller than that negative edge, and so we end up with the lower frequencies. Basically, if we have this relationship that omega hat equals minus k divided by omega, then we can make a plot here of omega hat as a function of omega, and so it's minus 1 over omega times some constant, which looks like this, right? It's just this 1 over x function flipped and then scaled. And here's omega p, which maps to minus omega hat p, minus omega p maps to omega hat p. Here are the values of omega for which our low-pass prototype had large gain, right? This is the pass band in the original filter. And so all these values of omega are going to be large values, going to be frequencies where the gain is large. They all map to these points out here, right? These green bars here. And so on every point on the frequency response of the transformed function corresponds to a point, a particular gain, a particular phase on the frequency response of the low-pass filter. But now all these points, which used to be the higher frequencies, which were the stop band, get mapped to these lower frequencies, these frequencies towards zero. So now the stop band is from 0 to omega p. And all these points up here that were the pass band with gains within epsilon squared of 1, and now frequencies out here above omega p. So we get a high-pass filter. So
What's the blue line?
the blue line here is just the actual mapping from this. The blue line is just this, minus omega p, omega hat p divided by omega, minus 1 over x, right? And so that's the actual point where if we have a particular value, if we've got this transformed system, we have some frequency, we want to know what its gain was at that frequency, we can literally just go here, look up the omega p that corresponds to that omega, look at the omega that corresponds to that omega hat, and then read off the h of s for the original filter at that frequency. I mean, that's what our transformation did, but we can relate them like that. And so the bottom line is we end up with a high-pass filter whose frequency response is basically, the inverse of the frequency response. The frequency axis is the inverse of the frequency axis of the original low-pass filter, in this way that frequency 0 maps to frequency infinity and vice versa, but frequency omega p maps to frequency omega hat p. So we're inverting two unequal intervals. One is finite, one is infinite. So there's a little bit of mathematical stuff that goes on, but basically, that's what reciprocal does for you, and it all works out. Similarly, if we wanted to, if we wanted to do a band pass filter, we could come up with some mapping here that took these regions here, this set of points here, and then map them to some limited range of points on the imaginary axis, and we could do the same thing for a band stop where we saw split them apart. The way that happens actually is that you end up doubling the order, because now you can't use a simple reciprocal here. You have to have some kind of quadratic thing. And so you end up with a bandpass filter that has twice the poles and twice the zeros of the low-pass prototype. But apart from that complication, it's basically the same kind of technique. And you could imagine doing it for more than one pass band, but that's a more exotic thing. But the principle is the bottom, again, it's quite unusual that you'd have to do this by hand, because once you understand the principle, it's easy to automate. And so basically we can get MATLAB to do this for us. But it is useful to understand exactly what's going on, because now there are various things you can understand about the properties of what this derived high-pass filter is going to look like. It's going to have the same number of ripples in the same order at the same depth. So that's why we're covering it. We're covering it in this kind of superficial way, the general idea without the hard details. Okay, so let's go through an example of that. Design a Butterworth high-pass filter with a pass band edge 1 dB down at 4 kilohertz and a stop band edge 40 dB down at 1 kilohertz. Okay, so we've got a pass band edge at a higher frequency than a stop band edge, so that's, it's a high-pass filter that we want. But otherwise, it's kind of similar to the example that we saw before. These specifications in terms of the high pass are now, we're talking about a transformed frequency axis. So these are omega hat p, omega hat s, if you like. So the way we do this is we're going to first design a low-pass filter and then put it through a transformation such that when we transform it, it'll give us the high-pass filter that we want. So we know that we want these, the omega, the prototype domain filter characteristics are going to be in terms of this omega p hat divided by omega space that we can map. That's how we map between them. So omega hat is that, and then omega hat is that of omega, and omega is that of omega hat, right? That's the way that k over x works. So we can just do that. We can work that backwards to figure out the omega s that will give us these results. In fact, of course, we can choose any arbitrary prototype reference passband frequency edge because we're going to scale it anyway. So we just say, okay, let's assume that it's 1, just for simplicity. So we've now got omega p, the prototype, but we still need omega s. So you plug it in to get that out, and it comes out to be 4, or minus 4, but symmetrically 4. So now we have our low-pass prototype, which is 1 dB down at omega p, which we took as 1, and then 40 dB down at omega s equal to 4.
Sorry, I missed something. What was the value for omega s hat?
Omega s hat is from, so here the specification gives us omega p hat and omega s hat. They're the actual, they're what we want to end up with. We're going to transform them from a low-pass filter prototype, but we're going to design that filter, right? We can build that however we want. If we had one already, then we'd have some particular omega p and omega s that might or might not work. But here we're going to design it so we can choose omega p to be whatever we want.
Okay.
So we just take it as 1. But then omega s has to be the thing that proportionally will give us the right ratio when we transform it. So we have these specifications. We can plug them in. Here we get the order has to be 5, which means that we can then plug that into our Butterworth h squared of s, h of s, magnitude h of s squared function to solve for the appropriate passband edge that will give us, this thing being 1.1 dB down at 1 kilohertz. So that turns out that the 3 dB point wants to be 1.4564, right? I mean, hopefully you can see what's going on here. I've just written down the actual equation that's going to solve that at the appropriate, we're trying to find omega c because that's basically the parameter that we have for our Butterworth filter, the 3 dB point. But we're saying, well, if it works, then this frequency omega p will give us this 1 dB down. This is like I took 1 dB and then turned it into linear units by taking 10 to the 0.1 divided by 20, but then I squared it, so it became 0.1 divided by 10. But that basically gives us an equation which then gives us omega c divided by omega p, or omega p divided by omega c, so we can get the ratio for omega c or omega p, and it's like 1.45, right? That makes sense. If the 0.1 dB point is 1, then the 3 dB point is going to be a little higher, so it's 1.45. And then we can get our low-pass prototype, we can get our low-pass polynomial out, and we can do the substitution to get the high-pass out. In fact, for Butterworth, we know what the polynomial is. It's this, circle with these odd-indexed poles at the radius omega c. I mean, normally you wouldn't have to do that, but it just happens that we know that. Here's a nice little expression to say that. But it's going to show up as a polynomial like this, with a product of a set of roots here, these poles, which are those red x's. And so then to get the high-pass filter, we take this polynomial, which would typically just show up as a s to the fifth plus s to the fourth plus whatever. I guess s to the a set of coefficients multiplied by polynomials of s. When we substitute in this s equal omega hat p on s hat, and then we rearrange to get a new polynomial. So, but if we do it here, then we just get this coming out, which if we multiply through by S hat to the n, then we get, this is now, these are more or less the roots, we get the actual zeros coming out here, and then we also get these, the poles coming out here. We also get this nth order 0 on top, which is, that makes sense. We're building a high-pass filter. It's a Butterworth high-pass filter, so it's smooth, but its gain probably is going to go to 0 at 0. So yes, this Butterworth filter has a stack of zeros at frequency 0, so at gain 0, at frequency 0 really does have a gain of 0, but they're all the same place, so they sort of, they grow uniformly. Whoa. Above that. Can you straighten it so it's still pointing at me? Thanks. Okay. And so, it basically does what we expect. And then we have a set of new pole locations which are now at the more or less at the reciprocals of the previous poles, which again means that they're sort of at higher frequencies rather than close to 0. So hopefully you can see that all kind of works out and makes sense. Of course, the proof is in actually building it and trying it out and seeing what its frequency response is. And when you do that, it works out. So here's how we can actually do that. It turns out that MATLAB not only will let us design these filters, but it will also even do the calculation of figuring out the order that we need, right? We had that closed form expression for the order, but it'll do all those steps. If you tell it the pass band edge and the stop band edge and the actual gains that you want at those 2 points, it'll figure out the order that you need for a filter. It'll figure out the appropriate 3 dB point that gives you that filter. So that's the but-ord routine. Then you plug those values into the butter routine with S to get an analog domain filter. Gives you the polynomials. And then MATLAB provides this LP to HP routine, which basically does this thing of substituting in for S and rearranging. You give it the original polynomial coefficients, and then the omega p, omega hat p, the product of those two constants, which is the thing you're scaling by. And it'll give you a new pair of filter coefficients, which are the modified filter. Now, here's the result of doing this for this particular domain. And here are the pole 0 diagrams. So actually, what's cute about this Butterworth high-pass filter is the poles are still on this semicircle. The actual poles stayed at a similar place. The semicircle may have changed in radius because omega p may have changed. But basically, they're still at the same pattern. But all that's changed is we've added n zeros here. And then those n zeros just happen to exactly balance things so that what was flat that rolled off now becomes something that has a high pass response and then is flat once you get above the cutoff frequency. And, I encourage you to try this out in MATLAB if you want to see how it works. Any questions about this stuff? Yeah?
We always use the dB value for RP and RS.
Right. So here, these are, as you've correctly observed, they're specified in dB rather than, say, gain. That is the convention that MATLAB has adopted. And, that's actually mostly, dB a much more convenient way of thinking about these things rather than thinking, oh, that's 0.01. In amplitude, you end up with getting a lot of low numbers. It's nice. It's numbers with a lot of decimal points. It's nice to have these in dB, and so this particular function takes these values in dB, but you could easily write your own function which took them in any other format. It's just their choice, and you need to check. I guess in general you should check the documentation of your function to figure out what those are. It's nothing particularly profound. Any other questions? Okay, so that's basically all we're going to do about analog filter design. And so now we've gotten through that. It's like, great, now I can I can come up with these Laplace domain polynomials that will give me analog filters with desired properties. But why was I doing this again? Okay, we're doing this because that's how we're going to build our discrete time filters. And the way we're going to go from these analog filters to discrete time filters is very analogous to what we did when we transformed from low pass to high pass. We're going to start off with our S-domain polynomial. We're then going to do a substitution that replaces S with some function of z to get a z-domain polynomial. But we're going to do it in such a way that this z-domain polynomial will have stable poles, assuming the S-domain polynomial had stable poles, and we'll have a frequency response that actually maps from the individual frequency points of the S-domain into the frequency, what works out to the frequency points of the z-domain. So what we're looking for is a mapping between S and z that takes this half plane and maps it to the inside of the unit circle, and takes this imaginary axis and maps it to the unit circle. And so that, that's not that difficult to come up with that transformation. The clever part is, like, once you do that, then if you give me a polynomial g of s, then I know what its g of z is going to do. And then if I've controlled the values on the imaginary axis for g of s, then I've got the same controls on the frequency response, the unit circle for g of z. But we'll talk about that on Monday. Any questions? All right, see you Monday.